Alejandro and, sorry.
I'm Andy, this is Joshua. Alejandro had to leave.
Okay, Andy and Joshua. And they don't, you guys don't have any slides, you're just going to
No, we can't talk.
No. So,
wait, hold on, let me give you a mic.
Yeah, can maybe kill the background on them or no?
Yeah, I can do that.
This is a good background.
Yeah.
Here, stand up here in the light. There you go. Share the mic. The mic's for the recording, not for the room, so just project your voice.
Okay, sounds great. Hey everybody, I'm Andy, this is Shashwat. Our goal for this hackathon was to utilize NuPIC in order to balance an inverted pendulum. So first we created the system where you have a cart on a track, and on top of that you have a pendulum that's inverted. After getting all the equations for that out of the way, we created a controller, and the controller's goal was to keep the system upright. So we managed to do that. We were able to introduce disturbances to the cart, and the pendulum was able to stay upright due to the controller. Then we decided to feed this data into NuPIC to see whether or not it could predict either the angle of the pendulum, or whether or not we could try and predict what force we would need to apply to the cart in order to keep it upright. That didn't work out so well, mostly because this is a time invariant problem and not one where having a history of states is actually useful. This problem can actually just be completely solved with your current state being angular velocity, current angle, velocity of the cart, and position of the cart, but mostly velocity of the cart. Yeah, add anything to that?
I mean, we played around with a whole bunch of different model params. We tried modeling them separately. I tried modeling them together, tried modeling different sets of them. That was really what we spent most of our time on, was just tweaking that aspect of it. And what ended up happening is we would have NuPIC watch the controller, and the pendulum would be like this, and then we would just study it for like many time cycles, and then we'd let NuPIC take over, and it would just so that's more or less what transpired this whole hackathon for us.
That's not what you wanted?
No.
But I mean, we kind of we figured it wouldn't exactly be perfect, because we knew it was a problem that could just be solved by the current state, but we wanted to see what would happen, see if it would work at all. Yeah.
Good try.
All right.
Thanks, guys.
Cool.
All right. Bear with me just a sec.
You're going to be the cameraman and the presenter?
Yeah, well, just in these two cases. All right.
You want me to run
Do
the
you want one
camera?
of us to go behind the camera?
I'm good. All right, here we go. All right, this is my hack. What I wanted to do was use the coordinate encoder and get in-game coordinates from Minecraft, which is a video game, for the current player location in X, Y, Z coordinates, and push them into NuPIC and get, well, I wanted to just see what I could do at that point. What I ended up getting to, because I've never created a Minecraft mod before, I just ended up getting an anomaly score for the current location or the current state of the player where they're at. And I really would try to get it back into the game, but I ran into threading problems. So all I've got is a little Python script here that's just a socket. It's an open socket, and creating a NuPIC model with the parameters for a coordinate encoder, which I'm going to start. And then I'm going to start the Minecraft game here. And we should see, let me get this up here. So we've got a connection. Hear the pretty music. So as soon as I jump into this world, you'll start to see, there we go. So I created this little path, and those hash marks on the right are how anomalous my current behavior is, my location behavior. So it's all anomalous initially. And I've got this track that I'm just going to run around a couple times. There we go. And I built this track out of bricks.
I like the thunder.
Yeah, I turned that on for fun.
Is it sort of the Frankenstein
All right,
effect?
so everything is anomalous at this point because it doesn't. Yeah, it just picked up some stairs. So I'm just still going to keep running. I haven't done the whole cycle yet, so this is just going to take a minute or two.
Is it tracking what you're moving?
Yeah, it's tracking XYZ coordinates. So as I'm moving, I've got a socket connection open from Java, pushing to Python, which is listening. We go
Yeah,
down
long
to this little
path.
cave. Yeah.
You could have made a
Nothing
shorter
else to
path.
do.
You could have made a shorter path and speed up.
I wanted an excuse to play a game. So
You're repeating now.
now I'm repeating, and you can see the anomalies are going down and down, and the further I go, it's exciting, isn't it? The longer I go, the better my anomaly score gets. So that's kind of what I wanted to see. And I really did not tune this very much. This isn't the geospatial coordinate encoder, it's just a coordinate encoder. So I'm not getting velocity information because I'm using a constant radius for the coordinate encoder. Whereas I could have done something smarter and based on my past movements increased or decreased the radius for the coordinate encoder. So let me show you what happens when I do this. Whoa! There we go. So that's not making sense, obviously.
Yes, you see anomalies.
Yeah, so there's higher anomalies now, it's a horse. But if I get back on the track, and this is kind of interesting, if I get back on the track and go backwards, it gets lower, it goes back to low anomalies, even if I'm going backwards. I don't know if that was, like with a geospatial coordinate encoder, this usually gets really anomalous when you go along the same track but in reverse. But it's not quite as anomalous with...
Because you didn't include speed in this?
Probably.
Well,
I'm not really sure, but it should.
no, it still
yeah,
should be
it's still
anomalous.
pretty. It is still pretty anomalous. Let me
You
turn
are
back
getting
around.
You're getting some. Yeah.
And so if I turn around and go back the other way, it's a whole lot better, right? Because I've done this twice now.
Are you going the exact same path, or is there
Yeah,
some
this
variation?
is just
There's a little bit of variation.
No, yeah, a little bit of variation, but it's just my human error that's causing
Yeah,
the
So
exactly.
you're
variation.
directing it.
Oh yeah, I'm moving
I see.
around there. See, I'm gonna break this stuff.
Right. All right.
Right, so I would call this a success. What I really wanted to do was get anomaly indications in the game by sending socket information from Python to Java, but which would show me, like a track. But
You've
Anyway.
shown that at least it basically works.
yeah, it basically is working. So this is just Cartesian coordinates and not geospatial coordinates, and it's working. So
Right.
I was happy with that. Okay, so that was mine, and now I'm going to talk about Austin Marshall's. His is called Shake Hack. So yeah, he couldn't be here for this, but he asked me to run through this.
I'll do the timing for you.
Okay,
I already started.
thank you.
10 minutes.
So it's this is on his GitHub Octopus Shake Hack, and what he did was he got information of earthquakes within a 1,000-mile radius of Pinger headquarters over the past 10 years. And he used the geospatial coordinate encoder, and at the time of the earthquake, the magnitude and the location, and passed those all through NuPIC using that encoder. He used the magnitude, I believe, as a direct correlation to the radius of the coordinate encoder. Oh, he didn't use the geospatial, I'm sorry, he used directly the coordinate encoder, just like I did with the Minecraft hack. But he had a variant radius based on the magnitude of the earthquake. So he asked me to show a video.
Would you expect to find patterns in
I don't know. What's going on?
So when's the next earthquake?
Well, it's
About
not
to
predicting,
find out.
it's just doing anomaly detection. So it's
Oh.
showing you how
that? Well, that's
anomalous it thinks that current earthquake is. And I don't think this has any sound. But here he is running the app, and he did this in sort of a clever way. He's got like there's a Redis service where that's getting the information and it's sitting there static, and the client is polling for it. And
how do you detect the anomaly here? How do you measure it? How are you showing it?
yeah, okay, so the red and black are highly anomalous, and the greenish yellow ones are less anomalous. I don't know the difference between red and black, but and the size of the circles indicates the magnitude of the earthquake. So I can't talk too much about this because he just kind of showed me, and I said, that's pretty cool. There's there's a lot of earthquakes right there, and was that in Nevada?
So the idea there'd be patterns in time of where these earthquakes occur.
Yeah, I think what he was explaining to me is that you would see a lot of smaller earthquakes in rapid succession in areas where there's likely to be larger earthquakes. And that would be the temporal pattern, if you will.
So it's a cool application, something I hadn't thought of.
So it's definitely
using
getting
in
more
coordinate.
green, right? It's
Yeah.
basically, yeah, I see. So it's basically saying they come in clusters,
Right.
Yeah.
and those clusters are near each other.
But some regions naturally have more, so it would adapt automatically to that. And so it would be, in each region, it would be relative to its past history.
You'd have to do some sort of statistical analysis on to show how well it's doing, or
Yeah.
it's kind of hard to judge based on this, other than you see greens.
It's definitely interesting the way he used the radius for the coordinate encoder to give it a magnitude dimension for the earthquake.
It just seems like simplistically it's saying whenever there's an earthquake near where there has ever been an earthquake before,
Yeah.
that's great.
Yeah.
It doesn't seem.
It could be.
No, but it should be more like they should occur in succession. If they were jumping
Yeah.
randomly over each other, that it would not. Think of them as a sequence. So there'd have to be, if you alternated all over the place, it wouldn't catch it. But it has to be basically saying, well, there's a little earthquake here, there's another earthquake near here, very similar to it. Well, it's a neat idea of how to feed data into the thing.
Yeah. So.
It's amazing how much green there is.
Yeah. Okay.
It's not good.
We done?
Yeah,
There's going to be an
Correctly
earthquake.
predicted there's going to be an
Yeah,
earthquake.
I think we're about done. So thanks, Austin.
Actually.
I'm going to get Yue and Chayton up next. They're the ones that got the table set up. This might take a couple minutes.
Wait, start the timer now.
No. But their team name is Chayton and Yue.
It's a whole new world.
Oh, it is a
A
whole
whole
new
new
world.
world.
And our team, our hack name is Whole New World. Team name is.
You're gonna have that.
And their team name is
the
Chayton
song
and
from
Yue.
Aladdin playing in the background.
A whole new world.
Yeah.
We barely had time to set this up, so we couldn't get the song.
So are we supposed to stand to see this?
You
Well,
probably
not
have
yet.
to.
Actually, we'll tell you when.
We
have a
need
slide.
to
Let's
talk
show
when you
one
do that.
slide and then do the demo.
Yeah, what's that got to do with the demo?
It's functional.
Connect that. Hello, I'm Chayton, this is Yue, and our hack is an application of the recent research we've been doing at Numenta regarding sensory motor inference and temporal pooling. So we'll show you a little robotics-based hack on that.
Yeah, so this is actually the first experiment we use real-world data and tested the algorithm. So the setup is very simple. We have a small router there. It has an IR sensor that's taking the distance between some objects. It has a range between about 5 centimeters to up to 30, 40 centimeters. So it also has a motor on the back. If you only look at the sensory part, it looks random because we program it to move randomly to sample to explore the world. But if you consider both the sensory input and the motor command, it contains some information about the layout of the world. And if you change the spatial configuration of the world, you might get a sense of this is a new environment versus the old one. And Shane will describe the algorithm.
Yeah, so a little bit of the theory before we show you the demo, so you kind of understand what's going on. What we're doing is taking this data from the sensor and the motor and feeding it in using a scalar encoder to get SDRs and feeding it in, both of them concatenated to layer 4. And so if you think about it from the perspective of this robot, what it's seeing is it thinks, okay, I'm going to move left now, and then it moves left and it senses how far away the object is using its IR sensor. And then it can turn right. I say, I'm going to turn right now. What do I expect to see? How far away the object is it supposed to be? And it can make a prediction. So in this case, layer 4 gets the information about the current sensor reading, how far away the object it's looking at is, and the motor command it's about to execute. And layer 4 basically learns those sensory motor transitions and learns to predict what it's going to see next, what the sensor value it's going to read next is going to look like. So if this was predicted by layer 4, if a transition was predicted by layer 4 successfully, it's learned that transition, then now layer 2-3 can pool over those predicted transitions, because now the world is more predictable. It can build a stable representation for that world. So layer 2-3 pools over it, does temporal pooling, and if it was unpredicted, then you'll see bursting in layer 4, and it'll pass through those changes. So what we hope to see is some stable representation once the world becomes predictable. So, and layer 2-3 is supposed to learn high order transitions, but we didn't test that part. Okay, so let's take a look at the demo. Disclaimer, this is a live robotics demo, so it very likely won't work. It did work yesterday in the room, and we took videos of it. But go ahead and stand up so you can see. All right.
So
this is.
So there are 3 objects. This is a robot. The sensor is in the front, so you can sense the distance to the object, and it will move around to sample the 3 objects.
So its movements are random?
It's random.
Its movements are random,
yeah.
Except with that, it
yeah.
tries to explore transitions it hasn't seen before.
Yeah.
So it's biased
Try
towards
not to
exploring new
restrict.
things. Yeah.
It's
Okay. It's initializing now. So
Okay.
what I'll do is put this down.
So we want to look up there, or we want to look over here?
Both.
Look right here.
Okay.
So we just tell you to do 30 random movements.
30 random movements. This is, by the way, nothing has been trained yet. The model is empty, hasn't learned anything yet at this point. So here what you're seeing is the representation in layer 4 in the middle, representation in layer 3 at the top, and the number of unpredicted cells in layer 4 at the bottom in that graph there. So it's starting to, everything's unpredicted. It starts to make some predictions, as you can see in the bottom graph there. And you'll see in the top layer, it made a sound. And it classified successfully this world. You see a stable representation in layer 3.
This is only showing you a subsample of the number of columns. So
yeah, this is just a subset of the number of columns. But you'll see some stability there. So now for this world, there's a stable representation it's built because layer 4 is able to predict.
Now we switch to a different
Now we go
world.
to a new world.
Uh-huh.
It's a whole new world.
The T world.
That was this one.
Yeah, I just changed the spatial configuration.
So it should look, yeah.
Yeah, we mark the lines so that we can go back to the first world.
Right, which
Later.
we'll do in a second. But it looks different, and we'll see what it sees and what it represents.
So it's going to go through the
So
same
you see
process.
it's resuming here, and you'll see that everything's unpredicted again because it hasn't seen this before. Layer 3, there's no stability. It keeps changing between the representations, and soon you see that it starts making predictions in layer 4, and it recognized this as a new world. And you see this representation here is stable, right? But it's different from this representation for the previous world. And you see in this classification here, it used to say 0 for the previous world, now it says 1. And it also played a different sound already.
Now we will go back to the first world to see whether it can recall the thing already.
Are you sure that that's exactly the first world?
We try to mark the positions.
Yeah, there'll be some small variations.
Yeah, can't be
there's
perfect.
noise in the sensors, the motors, and in our movements here. But hopefully it can be past that. It was this one. Was it? I mean, you.
I don't know. I think it is.
Yeah.
We'll find out.
Maybe we should change it to a somewhat new world.
We can always run it again, right?
Okay, so let's see what it sees.
Oh yeah. Oh yeah.
So it's making
So it's not perfect. So there's
Yeah, so the predictions, so there's noise, right? It's the predictions are, some of the
Yeah.
columns are still bursting.
Yeah.
Is that because it's just slightly different?
It's
than
slightly
the-
different, yeah,
predictions are
because
not
of noise in our setup.
So is it going to think of it as a new system, or is it going to think of it?
No, you'll see up there,
Zero.
right there. See, this was the representation I had for World Zero. This is the representation it now
So it's
sees.
interesting. So it's somehow generalized a little bit, accepted this noise, and says,
Yeah.
I'm going
Right.
to consider it. It didn't think of it as a new world. It just says a
Yeah. We can also
Wow.
try to do the anomaly.
Okay,
Yeah.
so we can do it. We'll do a little
We
anomaly.
run the same word again, but this time I will move one object away.
I'll go for it.
Yeah.
You can move it. While it's at the side.
I just take one.
Okay.
spooky new world.
See what. So some of the it's seeing there's some predictions you can see, but also some unpredicted things because it's right.
Yeah.
And you'll see there's no stable representation in layer 3, but should have maybe done more time steps.
You think it would learn as a new world now?
Yeah, but I think I didn't actually give it enough time.
There you go.
It might do it.
But yeah.
Close, but yeah.
I thought it was 0.
Just needed a couple more steps.
Decided it was 0. It was 0.
Let's do it. I'll do it by reset. A couple more steps.
2 minutes. That's Matt speaking.
But yeah, essentially you see that with the anomalous world, it wasn't able to consistently predict, so it didn't settle into a stable representation.
Is it still learning though?
Except
Still learning, yeah.
It's classifying as world 0.
it classified it as world 0 for some reason. So that's unexpected.
World 0 is the first word. Right?
World 0 is the first one. So that's interesting, yeah.
Yeah.
It classified it as
Pushing your luck
as the first one.
Yeah.
Demos.
Yeah, we were.
Never
We tried
do that.
something we hadn't tested yet.
Just stop after the claps.
But yeah, so there's the stability and distinction in layer 3, and that's
Okay.
what we're going for.
Great job. Okay. Okay, so give you a minute to clean up a little.
Which one?
These semantic hackers. Are you guys ready? Daniel McDonald and Mark Whalen?
Oh, yes.
Are you going to project?
Yeah, we'll plug in.
What kind of does this work?
It worked, yep.
Thank you.
Okay, don't start yet. Just
Ready?
Can I make one last comment? Totally forgot, actually. Really like to thank Ian for giving us this robot. We asked him for, we had this idea and he gave us exactly what we needed to execute on the idea. And he gave us time to fix, it wasn't working initially and he really helped us out fix it. So thanks a lot to Ian, if he's watching, for the robot.
very nice. Okay, guys.
All right, so our goal was to try to create a system.
Oh, could you introduce yourself?
Oh, introduce myself, sure. So I'm Daniel McDonald. This is Mark Whalen, and we are. Our team was the Semantic Hackers or something like that.
Now we want to be wacky sheep.
So our NuPIC Hackathon project was to try to figure out if we could generate a natural language request response hack, where we would give words into the system and it would come back with words back out at us. And our big goal was to try to make it so that the words that would come out would be grammatical sentences in some form. That didn't work out so well, but we had some success in some things that didn't work quite right. So let me try to describe a little bit of what we did. So this is, well, first of all, we'll demonstrate. This is our program that we created, and we can feed it in some text. What it does is it's going to take the words in that text and match them up against words that it knows in a vocabulary that we trained it on. So this is the Wizard of Oz example, right? So we took the text of the Wizard of Oz. We found that it has about 20,000 unique words in it that were also in the WordNet dictionary. So then for all the words in the input text that are found in our vocabulary, we build a fingerprint, a semantic fingerprint. So you saw Cortical IO's fingerprints. They're based off of a lot of background work in real high-level natural language processing intelligence. Ours is very, very simple. It looks at WordNet, maps the relationships in that network, and comes up with a fingerprint.
That's an SDR?
It is not as sparse as we would like it to be. So it's an SDR-like. It has the principles of an SDR, but it tends to have either few bits or lots of bits set. But that's an interesting point of what we did. So when we initially came here, I had really no idea how to make the fingerprints. So I was just saying, okay, we'll take all of my words and give them a unique bit, and that corresponds to a bit of meaning, and then build a fingerprint by sort of marking the bits for all the related concepts. It turns out 20,000 bits is kind of unmanageable. So we decided to use an idea that we got from the discussion on Friday afternoon, where you mentioned this, your geospatial encoder sort of randomly picks bits. And so we looked at that a bit and found out that, well, if we take each of our input ideas, each semantic concept, and just give it a random pattern of 5 bits, then anytime those 5 bits are set in our 4,000 bit string, then that means that concept. And then we can build our fingerprints by looking at all the related concepts in the WordNet tree and following some certain limits on that, and then setting all those patterns of 5 bits. And because of the sparseness of it all and the number of bits we have, there's very little overlap, and so you get this nice property of SDRs that comes out of it. So that's how we generated our fingerprints. We then needed to get a true SDR, which had we wanted to normalize it to a relatively same number of bits set for all of our concepts. So we fed them into the spatial pooler, fed our fingerprints into the spatial pooler. The spatial pooler, we tried to train it to learn our fingerprints, but that turned out to be completely unnecessary. And this was a great revelation for us, that if we used the spatial pooler just randomly initialized with no training whatsoever, it gave us a very good encoding of our concepts, or our fingerprints, as SDRs, which I completely did not expect that. So we ended up using that. No training, feed all of our fingerprints into the spatial pooler and remember the SDR that comes out as matching to the input one. In doing so, the first book we took, we had 62,000 input concepts from it. That was not the Wizard of Oz. And of that, 6% overlap came out. Right? So that means same fingerprint in, we get different fingerprints in, identical SDRs out. Right? So that means I've lost something in the process, but only 6%. And when we looked at the duplicates, they were nearly identical concepts and meaning. So we really didn't lose anything. Like adorable and endearing. They collapse together into the same SDR, but the words mean essentially the same thing. And since we're not encoding any lexical information into the fingerprints. So that was good. We then took the sentences from the Wizard of Oz, fed them through the temporal pooler after taking each word and building our fingerprint up out of our concepts. And then we tried to say, okay, now with this trained system, feed in a fingerprint for the text that's feed in the sequence of fingerprints for the text that we've got, and then generate out, let's sort of take the predicted output of the temporal pooler and feed and use that to decide the word that we print out. And we wanted to sort of link that up to a grammar structure, but we weren't able to get that working. And so now we're just basically printing out sort of related words. And then I'm getting lost in all of this. It's kind of confusing. So once we get the words out, we feed the output word that we select from the possibilities back into the spatial pooler to sort of drive the sequence. And that was the real idea, is in order to generate sentences coming out, there's got to be an outside process of some kind that is saying, okay, I've committed to this word, this idea in my speech generation, so that's got to restrict the future pathways that I can follow. So the temporal pooler is saying, okay, I matched a pattern and I see these possible directions I go from there. Once we pick one of those directions, now that sort of restricts further our future directions. And so we try to create that loop. And you see that here. We didn't get really good results. I think there's a lot of other tuning that we've got to do to try to figure out what's going on and why the concepts aren't really coming through as we wanted to. But we learned a lot in the process. It was a lot of fun.
Can you explain what we're seeing up there? Like, what is, like, is it the sentence generators is like the one
So means that the uhs are stuck in there when the output of the temporal pooler doesn't match anything. It's like we don't have a word for it, so right? Yes.
Yeah,
all this
so
works
are you
without,
taking the predictions from the temporal pooler and then feeding it back into the temporal pooler?
I'm taking the predictions from the temporal pooler, which corresponds to an like a union of the possible outputs. I'm then taking that, matching that to all of our sort of trained concepts and picking out the top matches, top 10 matches, and then from those top 10 matches, intersecting that with a set of expected concepts in the next in the sentence, and of that choosing a word. And then from that selection, then I've narrowed it down to a narrow concept that I committed to in my sentence, feed that in, right? So we're not taking the broad meaning that comes out, we're narrowing it through a filtering process and then feeding that in to drive the selection of the next word.
Well, the fact that you're getting good SDRs that way, it sounds like you tested it properly. That's pretty good.
Yeah, that was amazing. And really insightful. It's not really a power of the learning algorithm, but it's a power of the large number of bits representation of the data. Just not intuitive at all, but really neat.
We get all these results without having a connection to the internet.
Right.
Wow. Wow, that's very cool.
Cool.
I think with a little bit more time, a little maybe some suggestions, you might be able to make some progress on this. But, and that's a whole bunch of ideas that go through your head.
Right.
I think you're close.
I think very close.
Thanks, guys. Next up, HTML enclosure, Felix Andrews. Does this work?
Is there some key I should press?
Well, it'll come up.
Whoa.
That's perfect.
That's pretty impressive.
Yeah. That's always happens.
Stability.
It's
learning. So the resolution of my screen changed.
It might be the cable.
Oh yeah, maybe.
Room 5 good there.
Oh, it's nothing.
No, so.
It says it's weird.
Oh.
This happens every time. Oh, come on. Gotta back up.
That may have been a little loose.
Oh, I feel it. That was a great hack.
Okay. Ready when you are. Introduce yourself.
All right. So I'm Felix Andrews. I discovered HCM just this year, but I've been really getting into it and decided to do my own implementation, which is in Clojure. Clojure is a Lisp, a modern Lisp. It runs on a Java virtual machine and also cross-compiles to JavaScript. So yeah, good for one thing, creating online accessible implementations of it. And one thing I'm pretty keen on is visualization. So I have kind of background in data visualization, and I found that a thing called visualization-driven development is useful for me. So because this is such a complex system, there's a way to make this bigger, I think, sorry. It's such a complex algorithm, it's distributed. It really helps me to build up an intuition about it by being able to visualize it. So this is one example here of the algorithm running. On the left is an input field, so two-dimensional input field. The red bits are the on bits. And on the right is a field of columns. You can actually draw the proximal synapses between them there. And this is just running with a predefined deterministic set of patterns. So you can see that, obviously the sparseness there. You can also see the overlap scores of the columns, which is showing. I'm going to slow it down a bit.
Is that showing in grayscale?
Yeah, grayscale is the overlap scores. So it's just giving an indication of the spread of the proximal input field. You can also see the inactive proximal synapses, which also shows just the spread of the proximal field.
Why is it gray, black area moving around in it? Why is it, if it's just a bunch of columns, why isn't it overall?
Okay, because there's columns are connected locally to some part of the input field.
There's topology?
Yeah, there's topology.
Oh, wow.
So in this case, it's something like 20% radius.
Okay. Wow.
Yeah.
Pretty good.
So this is just to sort of build up an intuition of this stuff. Also, you can click on a column to exploit out the cells that are within the column. And in this case, it's a bursting column, so they're all active. And you can see, one particular segment is being learned, distal synapses there. If we keep running, hopefully it'll start predicting. Yeah, so the blue, you can see that. It'll show some blue dots, which are the predicted input bits based on the predicted cells. And yeah, so and it's the blue dots are actually from the previous time step. Okay, cool. So that's
so if it's predicting perfectly under the red, we wouldn't see it. Is that?
Yeah, if it was predicting perfectly,
purple.
it would be, it's overlaid, so it would be purple. And some of it's purple.
That's right. And then this requires some sort of reconstruction to bring it back from the prediction, and that's always tricky.
Yeah, so it's actually, you see the blue is actually like a continuous scale. So the brighter blues are connected from more proximal synapses from predictive cells, and there'll be a very light, almost invisible blue, which maybe just one or two cells are predicted.
Are you showing prediction on the right-hand box as well, or just?
Yeah.
I mean, we expect the prediction to be really good on the right-hand box, but on the left side, it might be dependent on the reconstruction methodology and so on.
Right. Actually, it's a bit alternative overlap scores. So, yeah, the purple columns here containing correctly predictive cells. Yeah, so in this case, 4 out of 5 are correctly predicted. Anyway, this is just basic sort of proof of concept thing. So let's rewrite this. I really wanted to try cortical I/O, and so sort of follow the same process. I'll just grab a bit of text. This is from Chetan's children's stories. Thank you. Oops. So I'll just enter some text. Put in my API key. Just a minute.
I'm not recording your API key.
Okay, so it's loading up. Now what it's essentially doing is building all the proximal synapses. That takes a while because there's so many columns, so many inputs. And this is this sort of standard cortical I/O field of 128 by 128. It's and I think it's something like 40 by 40 columns, so 1600 columns. It should take a few seconds more. And one thing I haven't done is what was mentioned yesterday of perhaps scrambling the cortical I/O input field to make it less spatially clumped, which may be important. Okay, so it's loaded up, and we can start to step through the words. So what it's doing, on the left here, you can see a sequence of sentences that are coming up in the text block, and within that we're stepping on a single word, and we're just going to keep stepping through, and it does a request to cortical I/O to load this stuff. Anyway, let's start running. And what it's also doing simultaneously, if there are any predictions made, which there aren't so far, you don't see any blue here, it will do another request to cortical I/O to look up the similar words. It'll sort of map back. Yeah. Anyway, it probably might take a while to start getting predictions on this stuff.
It's taking a while because you're making API calls in between words?
Partly. It's partly just the algorithm, because it's all running in the browser. It's all running in JavaScript. And this scale is non-trivial.
There's some predictions. Closure script?
Right, so Clojure can, with some minor modifications, compile into JavaScript and run in the browser. That's what this is doing. There's some predictions, yeah.
The only way it's going to make predictions is if you start showing enough text, it starts learning some of the patterns in the text, right?
Yeah.
So in the beginning, we wouldn't expect to see anything.
Yeah.
For a while.
Okay, here. Okay, here. So the word we're on now is just a full stop, end of a sentence, which I encoded. Obviously, cortical I/O doesn't have a full stop in it, so I just made that a random str to indicate the end of sentence. And it's predicting essentially the start of a sentence. What's going to be the start of a sentence? And it's predicting little, only, looked, something like that. Anyway, this only had 43 time steps so far. Now, I guess the point of this is to check that it's working, so debugging and just seeing that it's working. But then, because it's Clojure, we can go back to the Java virtual machine and actually run it there. which is what is more practical for actually real world. If you want to actually run over a significant bunch of text. So it's currently here running over the whole of Chaitin's children's stories. So doing how much? Well, the ones that you found for me, thank you. Or that I reused from you. So again, we can go in and just look up the predictions here while it's running. So we've got a prediction here saying very, or nothing happened. These are the predictions at that particular point that I asked for predictions.
We're at the 10 minutes.
Yeah.
Okay. So does it get good at all in the predictions, or is it?
I don't know. I just got this working. Like 5 minutes ago.
Well, you can leave it running again for a while and then tell us at the end.
Yeah.
So how long did it take you to write an HTML implementation and closure?
I guess I started in maybe March. So over that long.
And you've implemented all the what components of spatial pool, temporal memory?
Yep, I even had to go at temporal pooling.
Wow.
Although that needs work.
Wow.
Yeah.
Very impressive.
Cool.
Very good.
So yeah, also this code this project is called Comportex, and I'll get it into the Numenta contrib library.
Thank you.
Yeah, it's open source. So yeah.
Very nice.
Nice. Thanks, Felix.
Yeah.
I just pulled this out.
Yeah, just yank it out. It's not going to get any worse. Smart Harbor. We're going slow. Don't forget to talk into the mic and introduce yourself. And hopefully this works. Did it change your display at all when you plugged it in?
Yeah, the display is go to
Preferences, displays.
It's probably never case. Oh.
Yeah, this is what we did last time. Turn mirroring on and off. Yes. Switch groups to
What Felix did was played around with the plug in the floor down there, was it?
No, that's true. It's kind of hanging out of the wall. Alright, just unplug it and plug it back in.
Yay! That was good. Maybe?
Yeah. You might probably turn mirroring on so you can now if you want. Okay.
World's first one.
Alright, sounds cool.
It's in England.
Okay.
Okay.
Whatever you would.
So we're from the Netherlands. This is Daniel, and I'm Egbert. We're from a small company called PeerNect. We're a group of 5 people. In the Netherlands, we participated on a hackathon as well, a 24-hour hackathon, and we tried to detect an anomalous behavior of incoming ship traffic. So there were a couple of things we tried to do. One was see if the ship goes on another course, another course than we than predicted. we also wanted to see if it's another speed, so if it's closing up on a ship or a ship is slowing down, stuff like that. And also maybe if it's going into an area that it shouldn't be, for example like a windmill farm or any other structure or object. In the Netherlands we have a lot of water and also a lot of stuff in the water. So a couple of use cases we were thinking of was harbor overview, sluice security, and offshore security. Yeah, and Daniel will show a little bit of what we did here. On the hackathon in the Netherlands, we did some stuff, but we tried to go beyond that point here and try to see if we could feed some live data into it and see if we can get any results. And I will explain a little bit more.
So in Holland we had a couple of open APIs we could use, but unfortunately they closed them off. So we had to use our old data that we collected back then. But what we did is we took basically a month of data and then learned one model. Go ahead. Yeah, we took all the ships, we threw them in a pile, and then we learned one model of all these ships, and then we created on each of these ships we created a different model to predict if to see if there's any anomalies. And so yeah, we wanted to feed in live data, so we kind of simulated live data as you see here. We think we succeeded, but yeah, there are a lot more things to explore in the future, of course.
Did you use the Numenta geospatial encoder?
Yeah. Yes. Yeah.
You did. Okay.
So,
Okay.
yeah, that was
you can see some of the parts here. It looks like they're going across lands, but there are a lot of tiny ways that you can go to. Yeah.
So how do we interpret that? There's a line. What does the line mean?
I'll explain a little bit more. We trained the base model. We call it the base model with around 30,000 records, I think, of ship track data. And what you see here is, we took that as a starting point, and the green line indicates that it's seen the route before. So we trained it a little bit more a couple of times, and you see some anomalies, but most traffic, what you see here, the geospatial encoder of NuPIC says is it's seen before, and it recognizes as normal data.
What does the actual line mean? In the line?
It's the track that it took, and it's supposed to just leave a little trail behind the boat and then disappear. Yeah.
So the blobs are the boats. You can tell the direction by if the blob is on the left, it's going towards the left.
Yeah. Now we sped this up quite a bit, of course. Otherwise, you have to wait here.
So take an anomaly there. What do you think is happening? It's going at a different speed or a different route that nobody's gone before.
Or is that a false anomaly, or what does that mean? Yeah.
I think could be a false anomaly. We don't.
I mean, can you interpret it? I guess that's Thomas' question.
Yeah. So I think most of it's a little bit of noise from the NuPIC. So we tried with some different data, and you could clearly see it's anomalous. So you can clearly see it goes red like instant. And what you see here, like you see a little bit of yellow and a little bit of orange. That's a little bit of noise, but almost all traffic, because we also used this data to train it, almost all traffic got recognized. So NuPIC is doing a great job actually at recognizing all the tracks. Yeah.
Did you use the likelihood stuff at all, or no? The anomaly likelihood?
No, not yet, I think.
That takes care of some of the noise issues.
Okay.
But it'd be nice to test it is to actually throw some anomalies at it and see what happens. I don't know what would be a real anomaly. I mean, something going north-south instead of east-west or something. I mean, it'd be nice to
Or get on a boat and just start driving
drive in circles, drive a boat in circles or something.
Well, we threw in some tracks that we didn't record before, and they turned red. But then we wanted to have more tracks to show in the demo. But yeah, unfortunately, some things didn't work out as planned in the last hour or so. And that's why we're showing you this.
I mean, we've had these, in San Francisco Bay, we have a lot of boats, and we've had some that have gone too close to the bridge piers and hit the bridge. I mean, it'd be interesting if you could see that a boat was kind of veering off a standard shipping lane and knew that it was could get in trouble.
That's what we want to.
Right.
Let me zoom in a little bit. You can see how accurate it actually is. You can actually, you can see some of the tracks is not correct, but you can on some other data we have tried also.
So obviously you're not sampling very fast because you show at one point, and then you show at another point where it has to cross land.
But if the data was a little bit better, you would see it goes strictly. It follows the lines and the borders of the waterways very carefully. We've seen it with other data as well. So most ships leave the middle blank. So if a ship would deviate to the middle, NuPIC would see it instantly, and it's pretty accurate.
You tested that out?
Yeah, we tested it out. Yeah.
How often are you sending the data in?
We trained it with a TCP connection as well. So, but this is
the sampling is once a minute, once every 30 seconds.
Well, we threw in all the history first, and then.
How often is that history sample?
1 month of data is almost 6.7 million GPS positions.
Every how many minutes do you get a GPS?
Yeah, well,
every second. Every 2 seconds.
Every 2 seconds. So that's very fast.
It depends on
the speed of the boat. Depending on the speed, they have to give a frequent position.
They change it based on the speed of the boat.
Exactly. Yeah. And so in the Netherlands, they are obligated to give their position through this system. So depending on the speed.
We only had a fixed amount of data.
No, but the point is that if the boat's going faster, then they give more points a second?
Yes.
If it's going slower, they say don't bother.
Do you guys feed every point in sequence?
We try to use the pre-processing as well.
So you try to regularize the sampling rate? Normalize it? Something?
Oops, we're out of time. Sorry.
Yeah, we tried, but
we had some problems with the amount of data and getting it all to.
We should look at this more because we can get this data in San Francisco too. So
I have it all over the world.
Yeah.
Very cool.
Very nice. Yeah.
Thanks, guys.
Ship it.
In real time?
Yeah.
Okay, in and out is the team name. The hack is Temporal Memory and Racket.
So I'm from the East Coast, and whenever I come here to California, the first thing I do as soon as I get off the plane, stop it in and out, because we don't have it over there.
Oh, really?
I do. How does the connection?
Yeah, that's the one. Let's see what happens.
You gotta go in and out.
Yeah.
And also, I
that's good. That's good.
I expect this to be a pretty quick presentation as well, so it works on so many different levels.
Okay.
Okay, hold on a second.
Whoa. That was fast. Boom.
Just present from the. Oh, there we go. Great. whenever you're ready. Introduce yourself, please.
All right, so my name is Rian, and so the title of my hack is Temporal Memory in Racket. And so what I'm essentially going to be talking about is how one might implement the new temporal memory algorithms that Chaitin recently released in a programming language called Racket. So the reason I chose this hack is actually kind of selfish. I wanted to really get a good understanding of how temporal memory works and really dive deep into the algorithms, understand every intricate detail, because that's just how I work. And so one of the other sort of issues that I had, at least sort of coming from a mathematical and Lisp background in general, was I wanted to do something that was functional. And essentially, you know at every moment in time what your inputs are, and you can use those inputs directly. So essentially, it's all about purely transforming information from one data structure to another, and that was sort of really interesting to me. And what I absolutely did not care about was speed. So this is really a toy implementation. I just want to see something work and make sure that I sort of understand this entire process. So that was not an issue for me at all. So that's sort of why I favor clarity over speed, at least for now. So I don't expect this to be in any sort of commercial or production setting. And I guess the reason I kind of like Racket is, we had a presentation on Clojure, which is also another modern Lisp. Actually, Racket is being used right now across many different middle schools and high schools as their first programming language. So I feel like a lot of students are getting into this language very young. And I am also consider myself a novice programmer. I've kind of been at it for less than a year, maybe 9 months, and so the motivation for me to start programming was, on intelligence and these algorithms. So I had tried a couple of times, but finally I got to the point where, HTM stuff is enough motivation to really sort of kind of just go at it and learn to try and implement something. And so this is sort of my first program.
Whoa.
which
mine was Hello World.
Well, I did that too, but I don't know. But yeah, and so the other thing I want to talk about what makes Racket unique amongst not only the lists in general, but all languages, is that there's a really succinct, I don't know, natural language is very important to this community. There's a very succinct mapping between how we represent natural language and how we represent a programming language. So in essence, in Racket, everything can be thought of as a domain-specific language, as I'll sort of get into briefly. And the idea is that over time, essentially, you end up creating code or program that essentially fits or maps to your program. So it's essentially you're evolving code to fit or solve your exact problem. And that, I think, is pretty cool. So those are the whys. And now I wanted to just touch on some of the differences between the implementation that I'm working on and Chaitin's implementation in Python. So there are not that many differences. I essentially wanted to make sure that the mapping was as close as possible, but there are some slight deviations. So first, in Racket, there are no classes at all. So like I mentioned before, it's just pure information moving from point A to point B. So that's the first thing. The other way is sort of how you iterate your functions. And or at least I like recursion. Recursion is kind of, you have a love-hate relationship with it. Some people love it, some people hate it. Actually, there's this cool quote I found: "To iterate is human, to recurse is divine." And it just kind of goes along with sort of your own philosophy. But you can do a lot of really interesting things with different types of recursive techniques that are a lot more difficult to do with using different types of loops. And the other thing, and kind of what slows this implementation I'm working on, is that I wanted one uniform data structure. That's it. I didn't want any sort of confusion, and so I went with the list because Lisp is actually short for a list processor. So just that was pretty important to me as well. And in this implementation, learning is always on, and I know that you have the opportunity to turn it off, but I just didn't get time to sort of think about that yet. But we'll implement that hopefully pretty soon. And many of you guys probably know this guy, Linz, and one of the things he says is talk is cheap, show me the code. So I don't normally like to show code, especially in a presentation, but I think it's just going through a couple of just the main function, a couple of, let's see if I can get this working. Couple of the things, and show you kind of what I mean by sort of kind of clarity and a really nice mapping from natural language to programming language. So this is essentially, the idea is, given your main computing function for how we do temporal memory, it should be the exact same, given the same input, you should get the exact same output as the way it's written in Python. So one of the main differences I talked about is sort of no classes at all. So the way we kind of get rid of this idea of not needing classes is essentially at each moment in time feeding in all the neurons and their associated segments. And so this is obviously very long and very tedious, but you kind of know at any point in time, where your data is and sort of what the state of your temporal network is. So that's sort of one of the major differences. The other one is just kind of the use of the way functions are defined locally here. So just kind of, you can compute your current active neurons they're used to compute the active segments and so forth. You can kind of nicely see how this stuff just moves from start to finish. Let me get through that. And just the last thing I wanted to touch out without going into a lot more detail is pretty much how you learn in this system. So basically, instead of, we basically only have these 3 learning update functions. And the idea is that you just essentially, as you recur, here's kind of the natural recursion. So we compute, so basically recursion is, just for anyone who's not familiar with it, is once you define a function, you call that same function within the function. So what we're doing is we're essentially not worried about the state of the program at all. And the only thing that we actually output is what goes up into the CLA classifier, so the active neurons. And the rest of the outputs kind of stay within the recursive system. And only, we only need them in order to actually, as the data sort of flows from your sequences. So this is how we kind of continue the process. And I think that's all I got and what I wanted to get into. And so that's it.
Is it running?
It is not running yet. But I know that it will run. I mean, I've tested all the functions. I just haven't gotten to testing this one big function.
You can't expect them to do HTML and Racket at a hackathon.
No, I didn't know. I just was on the edge of my seat.
but it should run. I'm pretty confident it will.
All right. That's got to be the gutsiest first program to write I've ever heard.
Did anybody write Haskell HTML?
I'll get to that next.
Oh, great. Okay. We're at the halfway point. Let's take a 10-minute break.